Today, I'm looking at potential sources for use with spectrum analyzers. Specifically, what I'm trying to find is a source of wideband energy that you can use to determine the frequency response, where you send a signal into one side and you measure the transmission with a spectrum analyzer on the other side of a unit, generally a piece of RF equipment. Could be a cable, could be an attenuator, could be an amplifier, lots of different possibilities. So on the screen what you see is an ordinary square wave. This is 5 megahertz, 200 millivolt peak-to-peak square wave. And up here on the spectrum analyzer, you see the normal spectrum. That is the fundamental and all of the odd harmonics. Now, this is not an especially good type of signal to use for what we're looking for, because what we want is something that produces relatively constant output over a band of frequencies. And the problem with a square wave is that each succeeding odd harmonic gets lower in amplitude. The second problem is these are spaced quite a ways apart. So for example, you have a 1 megahertz base signal, the third harmonic is going to be at 3 megahertz and so on. And often that's too far apart to be useful in looking for things like reflection coefficients, or more importantly, areas where there's less gain or more gain than normal. In other words, you don't want to find a something that's in the middle here and miss it because you're not checking at that frequency. So let me show you my thoughts on the matter, and then I'm going to be going through a series of steps trying to find an ideal source. One reason I'm doing it this way is at the same time that we'll be looking at noise sources and things of that sort, we'll also be able to talk a little bit about a process. That is a process for how you can look at the possibilities to solve a problem in a wide-ranging way. In other words, a bigger box, thinking outside the box. So first, let's take a look at what my original thoughts were. And if you have some comments or thoughts on this, I would certainly appreciate them. Put them in the comments of some other things we might be able to try. Going back to this picture again, what we're trying to do is to generate a signal on the input of some kind of device. This can be a transmission line or an amplifier or a mixer or anything that we want to measure the transfer characteristics. We want to generate a wideband spectrum that passes through the device under test, and then we want to measure using a spectrum analyzer on this side how much of that signal comes through on the other side and at what amplitude. In other words, if this is an amplifier, then we want to know how much amplitude, how much does it amplify at each frequency. Or to use the S parameters that we have talked about in some other videos, what we're measuring is S21, which is really just the transfer function of this device under test. By transfer function, we mean how much of the input transfers to the output. So that's what we're looking for, is a good wideband source here that we can then view on a spectrum analyzer over here. So here are the thoughts, some things that I might try. The first is we might try a signal generator. Now by that I mean a generator that generates an RF signal, and perhaps we can find a way, either by modulating it or by some other method, to cover a band of frequencies. Probably not going to work too well, simply because you could do it this way, but you'd wind up, I think, plotting a point and then moving the generator, plotting another point, and so on. We'd like something that'll show us a band of frequencies, so probably not an ordinary signal generator. Next possibility is a sweep generator, and you may have seen me use this before. In fact, in some of my earlier videos, I used a sweep generator. As long as you use the max hold function on the spectrum analyzer, you can sometimes get a pretty good frequency response or Bode plot for an RF device. But the problem is you're depending on the sweep generator happening to be at exactly the right frequency when the spectrum analyzer is also looking at that frequency. And you can improve the statistics by averaging over a long period of time using max hold and so on, but pretty inconvenient. Third way is to use a function generator. Now, we'll come back to this one. The traditional method is to use a tracking generator. That is, a generator that is built into the spectrum analyzer, or is at least synchronized with the spectrum analyzer. For this to work, you have to have a way to synchronize the generator frequency with the spectrum analyzer frequency. I'm sure that if you've watched any of my or anyone else's videos on using a tracking generator with a spectrum analyzer, you're familiar with this, and we won't talk any further about that. And then finally is a wideband noise source. And one of the reasons that I'm interested in this, the wideband noise source, is it's something that might be useful with the software-defined radio spectrum analyzer that I talked about in an earlier video. And so perhaps we'll follow on to this video, maybe using a wideband noise source as a source of spectrum. Okay, I said we'd come back to the function generator, so let's do that. One thing that occurs to you right away is, since a square wave produces a series of harmonics, you might use that. Well, we've looked at that already and seen some of the downsides. So the next thing that I'd like to look at is what is called a sync function. And only the better arbitrary waveform generators tend to have this function. So it's not a really good general purpose solution. But it's interesting enough that I think you might like to take a look at it. So let's do that. This is what a sync function looks like. Now let's zoom in a little bit here first. And let me expand the time base of the oscilloscope so that you can see what the sync function is. It's a pulse that has a somewhat triangular shape, and then what appears to be ringing on both sides. That is, the upper sideband rings, or the upper point. We'll see in a minute what the sidebands look like on the spectrum analyzer, as well as below. Now, this is a useful mathematical term because it can be used to do analysis of transfer functions. And so some arbitrary waveform generators will generate a sync pulse. Now in this case it's the same frequency. 1 megahertz is the basic frequency. In other words, there are 1 million of these pulses every second. So let's take a look at what it looks like on a spectrum analyzer. Here is the same spectrum analyzer connected to the same signal that we looked at earlier. Things are looking up. At least we have even spectrum across a broad range. We still have the problem that the it's only occurs, that is, the frequencies only occur at a particular step. But we do have a fairly constant, and this is 120 megahertz out here at the right, and basically 0 at the left. So out to close to about 100 megahertz, we have from 0 to 100 megahertz a pretty good flat response. So this is a possibility for use as a spectrum source. The other things we might try, though, are noise sources. So let's take a look at that. One possible noise source is a function generator itself. Just as the good arbitrary generators generate noise, generate sync functions and others, they will also generate a noise function. So what I'm going to do is take a look at that. In the case of the sync function, well, all of these so far, the signals have been generated by a siglant SDG2122X, which you've seen previously in some of my videos. It's been out for a while. But another source of noise that I would like to try is one that people have had good success with in many cases, and that is using a ZENER diode. Now, when you reverse bias a ZENER diode, because of the way the diode is made, it tends to generate a pretty broad band of noise. So it has the first characteristic, wideband. Unfortunately, that noise is at very low amplitude. So we're going to look at amplifying that low amplitude wideband noise with a transistor and perhaps a low noise amplifier, a little more expensive. Now, none of these are really proposed as a good source for spectrum with a low-cost spectrum analyzer. We'll get to that perhaps at the end of this video, or perhaps in a future video. What we're looking at here are the characteristics that we might want to pay attention to in evaluating noise sources. Now, I have a noise source on order. It isn't here yet, made by a company in the Ukraine that sells on eBay. Except for the delivery time, it looks like a pretty good device. And when it gets here, I will be using that instead of an amplified reverse ZENER diode. However, I will tell you that that noise source I know actually is nothing more than an amplified reverse biased ZENER diode as the source of noise. So we'll get there eventually, but for now, let's first look at noise generated by a function generator, and then finally we will look at using a ZENER diode with a couple of different kinds of amplifiers. So I've set up the siglant, this once again is the SDG2122X, for a 100 millivolt standard deviation noise source. Now, I won't go into this because each generator is going to be different. You'll have to look at your instruction manual. And once again, as I say, I'm using this because I want a good source of noise that I can use to manipulate in various ways to see how useful it is as a spectrum source. So now let's take a look first at the oscilloscope and then at the spectrum analyzer. Here is what the noise, 100 millivolt standard deviation noise, looks like on the oscilloscope, and here on the spectrum analyzer you see just a straight line of noise. Now what I'm going to do is turn off the output of the generator, and you'll notice it drops to minus 70 dB. I'm going to turn it back on, and you see we get about probably minus 35 dB. Now, we could turn on averaging, but for right now, we're just looking at the ideas here. Now, this is the same stop frequency I was using earlier of 120 megahertz. Let's increase the stop frequency to something like 500 megahertz. And there you see that we're getting a pretty good, this is now 500 megahertz. So this is 250, 200, 150, 100. So out to about 150 megahertz. Let's change this to 200 megahertz. Okay, now it's 200. So this would be 100, out to about 120 megahertz. We get a pretty good flat noise signal. Once again, we'll turn this off. You see it goes to 0. So this is one possibility. The next thing we're going to try is a ZENER diode reverse biased. Now, I haven't changed the spectrum analyzer at all. This is exactly the same. That is, it is going from 0 to 200 megahertz. What you see here is a noise spectrum that runs out to about 50 megahertz and then begins to fall off. We'll look a little more carefully at that in a second. What it looks like on the oscilloscope is just seemingly random noise. And the circuit is there, the breadboard is over here, and we'll talk a little more about what we are doing. But what we are going to be trying to do is to see if there is a way to broaden out the frequency response, pardon the rapid camera movement there, to widen the bandwidth of this noise source. That is, what we would like is something that will at least go out past the 150 megahertz range so that it's useful out to, say, 2 meters for an amateur radio operator. The wider the better, because a nice flat noise source going out to 400 or 500 megahertz would be ideal. But I will tell you that the noise source that I ordered from Ukraine claims to go out to several gigahertz. So we'll see when it gets here what it actually does. But lest you think this is an artifact, I'm going to turn off the power supply now. And you see that now there is no, by the way, these are FM signals. Remember, this is 200 megahertz, so this is around 100 megahertz. So those are FM broadcast signals that are just getting into my breadboard. The power's back on again. So now you notice that we're only getting about minus 50 dBm of power, and it's only going out to about 50 megahertz. Let's see if we can do better. So what are the things that we could try? Well, we could try varying the bias voltage, that is, the voltage flowing through the ZENER. And I've moved that around a bit using a potentiometer that I have in this box, and determined that about 150K generates the most noise, the broadest frequency of noise. So I've put a 150K resistor in here. The next thing is I tried some resistors varying this. I put a 470, which is the figure for the resistance of the circuit I got off the web. Then I went up to a 680 and finally to a 1K. And then finally I replaced the 3904 with a, see if I can read the number on it, S9018. Probably can't read that. Let's see if there's get a little more light up here. An S9018. which is a higher frequency transistor. It's a general purpose replacement used in transistor radios for an FM oscillator. So it has a higher transition frequency, FT. The 3904 typical FT is somewhere between 100 and 300 megahertz. The 9018 has an FT close to a gigahertz. If I can't remember, well, let's take a look at the spec sheet on that for just a second. Yes, here is the S9018 spec sheet, and down here is the frequency FT, current gain bandwidth product, with a VCC of 5 volts and a collector current of 5 milliamps. It runs between 700 and 1100 megahertz for the FT. So about 3 times the frequency response, but much lower gain. The typical, let's see, what is the typical collector? HFE. Yeah, if you see here, some of the better ones have an HFE in the 130s. I measured these. I think the ones that I have are H, because they run between 90 and 140 or so. I have a whole box full of them that I bought as part of a kit. At any rate, they're a very general purpose transistor, pretty cheap. I think 40 cents each or something like that. I paid even less because I bought a pretty good sized kit. So those are some of the changes I made, and here are the results I got. Now on the left is the type of transistor, and for the first 3 rows I just used the 3904, and I tried the 470, the 680, and the 1K. You get a fair amount of noise at 5 megahertz, and you may notice when we get down here to the 9018, you get a lot less noise at the low frequency. But in a second we'll kind of look at these numbers, and you'll see that the advantage of the 9018 is you get a lot flatter response. So 470, 680, and 1K. After I had determined that, I left it at 1K. I tried these other values with the 9018, and frankly, because it has a much lower current gain, you really do need the 1K in there to get enough noise to be useful. So, but notice what happens here is the noise falls off dramatically as you go up in frequency. So you get only about half as much, and remember this is dBm, so these are dBs, that is logarithmic scale. So it really falls off quite a bit. You may notice that it stays about the same at the high end, and that's because, frankly, that's very little more than the circuit noise. But at 5 megahertz, as you raise the resistance, the actual RMS noise falls off a little bit. But that's actually good, as I say, because what you want is something that's a little flatter if you're going to use this as a spectrum source, say with a spectrum analyzer in place of a tracking generator. But it's very clear that the way to go here is with the 9018, because notice that with a 1K load resistor, we start out at minus 27, but we only go down to minus 31 at 20, and only minus 39 at 40 megahertz. So with the 9018 in there, this noise source will be useful out to around 40 megahertz, which, remember what I was saying I was looking for, is something that might be useful to a radio amateur, for example, that would cover the HF band. Now, it would be nice if it would also go up into the VHF band, but I'm afraid that is pushing it for a circuit this simple. And The answer to that, I believe, is a commercial noise source that you can obtain at very low cost on eBay. So that unit has just arrived. So let me get it out and we'll do a few tests on that. So here is the noise source that I bought. It takes 12 volts on the left, and by the way, if you should of course check this if you buy a unit like this. I paid just under $20 for this from Ukraine, including shipping. But for mine, the center of the 12 volt input was positive. So I have that hooked up, and I'll show you that in a second. And then over on the right hand side is the RF out with an SMA connector. So right now I have this source connected to a Siglant power supply that you see over there with 12 volts. And then it's connected to the Siglant spectrum analyzer over there. So let me move the camera and line this up and we'll take a look. So what you see is the Siglant set to its full span, which in this case is 3.3 gigahertz. And as you can see, I'll leave it zoomed out for a second, we'll look more closely in a minute. At the very low frequencies, you get, I guess about minus 10 dBm of noise power. But as you see, it continually falls off until out here at 3.3 gigahertz. Now this is advertised to 3 gigahertz, so maybe it's a little beyond that. But basically, it drops below minus 40 dBm before it gets to 3 gigahertz. We'll look at exactly what the value is at 3 gigahertz in a second. But unfortunately, this is not a very good source for a wideband measurement. Now, if you take a small or narrow segment of this, you might be able to, the slope might be manageable. But this is not a replacement for a calibrated source. It would be useful, in my opinion, in looking generally at filters and amplifiers and things of that sort to get a general idea for their frequency characteristics. And I plan to use it in a few experiments with the SDR spectrum analyzer, the one based on the RSP1A that I have talked about in a previous video. And in that situation, what I'm going to try to do is figure out whether there might be a way to level this a little bit, perhaps by providing an amplifier that tends to amplify more at the high frequencies than the low and kind of balance it out. But anyway, that's for the future. For right now, I thought you might like to take a look at this. And now what I'm going to do is I'm going to put a marker on the screen and show you what the actual output level is at its lowest frequency, which is a megahertz, and its highest frequency, which is supposed to be 3 gigahertz. I have a single sweep on the screen and a marker at just under a megahertz. Let's zero in on that. And you see it's producing at 920 kilohertz. It's producing minus 13 dBm. We're going to go up to 5 megahertz now. And it's 10.89 dBm. So now let me reset it and we'll go up to 3 gigahertz and see what the noise output is there. Okay, we are now at 3 gigahertz and the output is minus 42.57 dBm. Let me show you what that looks like on the screen. And what I have is a sweep from 2.9 gigahertz to 3.1 gigahertz, so 3 gigahertz is right in the center. So, as I said earlier, this is not a calibrated noise source, and frankly, calibrated noise sources of this frequency range would cost at least $1,000. Depending on how well calibrated they are, but so you don't expect that kind of thing. But the question is going to be how useful it will be when used in with a spectrum analyzer like the SDR Play RSP1A spectrum analyzer software with the RSP1A or the RSP2 or something like that. So that's for the future. For right now, I have concluded what I wanted to get done in this video, cover a number of potential spectrum sources, and in a future video we'll be using these spectrum sources, or at least one of them, probably this one, maybe something else as well, to do some experiments with the SDR spectrum analyzer. So look forward to that. I hope you've enjoyed this video. Once again, if you have some suggestions about things you'd like to see, either in this topic or some other, put them in the comments. I do read comments. I don't always respond to comments, though I do try to find those that might be of general interest and respond to those. But if you want to make some suggestions about future content, do so there. And I hope you've gotten something out of this. And more than important than that, I hope you'll stay tuned for some future videos. And in the meantime, have a nice day.